The Amsterdam modeling suite has several built-in features for the analysis of molecular dynamics trajectories. How one of these features, namely the autocorrelation functions interface, can be used to estimate the viscosity is what I would like to demonstrate to you in this video. The video is based on a recent step-by-step tutorial to which I have put a link in the video description. The viscosity can be estimated using the Green-Kubo relation. Here P alpha beta is an off-diagonal component of the pressure tensor, and the function under the integral is an autocorrelation function with the average taken over all time origins and off-diagonal components. We begin by importing a simulation box filled with several benzene molecules. A link to the structure is found in the video description. Next, we are setting up an MD calculation with a high frame rate of 1 frame every 2 iterations and request to calculate the pressure for every frame too. We choose a Nuse-Hoover thermostat and set it to 298 Kelvin and a total of 100,000 steps before saving and running the calculation. Once the calculation is finished, we can open the trajectory in AMSmovie. Let's first check if the simulation did equilibrate successfully, and indeed, after around 3,000 to 4,000 steps, the potential energy seems to fluctuate around a constant value. Now calculate the autocorrelation function. Open the autocorrelation function menu and choose to discard the first 4,000 steps as those were not fully equilibrated. As a property, we choose the vector elements 4, 5 and 6 from the pressure tensor, which are the off-diagonal elements. Following the advice from the tutorial, we set the max ACF step to 3000 and start the calculation. This brings up several graphs in AMSmovie. The bottom graph contains the integral of the pressure tensor autocorrelation function. In the ideal case, this graph will converge to a constant value as the time approaches infinity, though this usually requires very long simulations. In this case, the integral seems to converge to a value of 1.22 10 to the power of minus 9 in atomic units. Since we know the volume, we can now calculate the viscosity with the Green-Kubo relation. In this case, we get a value of 0.61, which is reasonably close to the experimental value of 0.5 megapascal seconds. For a more realistic production run, one will increase the simulation cell and the number of simulated steps, among other tweaks discussed in the tutorial, to achieve an even better agreement with the experiment. That's it for today. I hope you found this useful, and make sure to check the online tutorial for best practice advice and an example of an automated workflow for viscosity calculations.